Hello everybody, it's Mrs. Pound and I'm here with the last video for Chapter 12 on gases from BGAU Chemistry's 5th edition. So we're going to finish this chapter by talking about the last section, section 12.3 on gas stoichiometry. So our objectives today are to state the law of combining volumes, explain why the kinetic molecular theory is limited in its ability to describe real gases, use the ideal gas law to perform calculations, and predict the amount of gas in a chemical reaction by using stoichiometric calculations. Let's begin with the law of combining volumes. This law states that under equivalent conditions, the volumes of reacting gases and their gaseous products are expressed in ratios of small whole numbers. Oh, this sounds kind of familiar, doesn't it? Because the ratios of these small whole numbers are the ratios of the moles of reactants to the moles of products. So now not only do the coefficients out front in a balanced equation stand for moles, it also stands for volumes. So an example would be 1 liter of hydrogen gas reacts with 1 liter of chlorine gas to produce 2 liters of hydrogen chloride gas. Or we could also say, as we're accustomed to, 1 mole of hydrogen gas plus 1 mole of chlorine gas yields 2 moles of hydrogen chloride gas. So that leads us to Avogadro's law, and this says that the volume of a gas maintained at a constant pressure is directly proportional to the number of moles of gas. So remember Avogadro's number, a mole of gas. So guess how many molecules or particles are in, you probably guessed it. Molar volume is 1 mole or 6.022 times 10 to the 23rd particles of any ideal gas at STP occupies 22.4 liters. This is going to be an important fact that we're going to be using in calculation. So now 1 mole is 6.022 times 10 to the 23rd particles, and it's also, if we're talking about a gas, 22.4 liters always. So we can use this fact to figure out what volume will 6.7 moles of ammonia occupy at STP. Well, we start with what we're given, 2.67 moles of ammonia. And we now know that 1 mole of ammonia is 22.4 liters of ammonia at STP. This is an important thing. This is the value at STP. And we get 59.8 liters of ammonia. So that's how many liters, 2.67 moles of ammonia will occupy at STP. Now let's take a look at some assumptions the kinetic molecular theory makes about ideal gases, because do gases act ideally? No. So they do not always apply to real gases. So let's take a look at some cases. The first is the assumption that the kinetic molecular theory assumes that gas particles are tiny and have great distances between them. In reality, real gases can be made of large particles and can be close together at low temperatures or high pressures. The second assumption is the theory states that gas particles do not interact with each other or with the walls of their container except during momentary collisions. Well, the reality is real gases do in fact interact to some degree. And if the pressure is high enough or the temperature is low enough, the gas particles will begin sticking together. So they may condense and become a liquid, or they may even start to react under high enough pressure to form new compounds. So that leads us into the ideal gas law, PV equals nRT. And this should look kind of familiar, because if we divided T over here and put it over here, we would have PV over T, which fits in with our combined gas law equation we were already using. Now, the big difference here is when we use the ideal gas law, we are just dealing with one set of conditions. When we're using our combined gas law, we're dealing with two different sets of conditions. So that is how you will differentiate which you use. Ideal gas law, one set of conditions. Combined gas laws, two sets of conditions. So the N is the number of moles. R is the universal gas constant, which is 8.31 kilopascals times liters over a mole times Kelvin. Now, this is not something you have to memorize when you use this on your test or a quiz. I will give you the value you need depending upon what you're given, especially for pressure. That may change. So a problem we might use for this is how many moles of a gas are present in a 3.32 liter sample at 154 kilopascals and 29 degrees Celsius. So here are the values we're given for volume 3.32 liters, pressure 154 kilopascals, temperature, we have to convert the 29 degrees Celsius to Kelvin. And when we do that, we get 302 K. And I give you the R value. Now see here, there's only one set of volume, pressure, and temperature numbers. There's not two sets, so that's why we use this equation. So we write down our equation, PV equals nRT. We make our substitutions. So I just substitute in those numbers that I just wrote down. So pressure 154 kilopascals for volume 3.32 liters equals N times the universal gas constant that I gave you times 302 Kelvin. Again, make sure the temperature is in Kelvin. When I rearrange and make sure that my units cancel out, I am left with moles, and this will flip up to the top because it's 1 over 1 over a mole. So when I do that, it actually flips up to the top here. And so my answer, the number of moles is 0.204 moles. Now, another type of problem we might see, this is going to combine gas stoichiometry with the ideal gas law. So when 7.15 grams of calcium react with water to form calcium hydroxide and hydrogen gas, what volume of hydrogen gas will be produced at 350 Kelvin and 115,511 pascals? So the first thing we have to do is we see that we're given a certain mass. We have to find the number, but to do that, we need to write a balanced equation. And so our balanced equation, they said that we have calcium. Calcium is a solid at room temperature, plus water, which is a liquid, gives us calcium hydroxide. Now, don't forget to look up your oxidation numbers for this. Hydroxide is a polyatomic. Calcium +2, hydroxide -1, so that's why we have the 2 back here. That is soluble in water, plus hydrogen gas. Remember, hydrogen gas is a diatomic. Now, I did go back and I had to balance this and put a 2 in front of the water, because remember, when we're balancing water, it's helpful to think of it as HOH. And if I do that, I realize that I only have one OH here, but I have 2. And also I only have one H out front and I have 2 here. So putting a 2 out front balances that. Now we need to know the number of moles of hydrogen gas produced by the reaction. So we convert from the known amount of calcium. We start out with 78.5 grams of calcium. We now have to convert to moles. So we know that the molar mass of calcium is 40.08 grams from our periodic tables is 1 mole. Now we can go to our equation and get our mole ratio, and we can see from the equation that it is in a ratio of 1 to 1, so 1 mole of calcium to 1 mole of hydrogen gas produced, and canceling my units along the way yields 1.96 moles of hydrogen gas. Now I have this value that I can now use in my ideal gas law formula. So we use the ideal gas law formula to find the volume. So first, write your equation, PV equals nRT. Our values that we have now are 115,511 pascals for pressure. Volume is what we're looking for. And from our calculations, the number of moles is 1.96 moles. I give you the R value, and T is 315 Kelvin. So write down your equation. Make your substitution. So for pressure, 115,511 pascals times the volume, which we're trying to find, equals 1.96 moles times R times the temperature of 315 Kelvin. So I rearrange. I divide both sides by my pressure and rearrange. This is what I get. I should also check, let's see, pascals cancel out, moles cancel out, Kelvin cancels out, leaving me with liters for the volume. So cross those out. So I get the volume is 44.4 liters of hydrogen, which should make sense to us because we know that at STP, and it would be very close to STP, that the molar volume is 22.4, and I have 2 moles of this. The pressure and the temperature are a little off, but this does make sense that it would be about double if I have 2 moles, about double the molar volume. Now, the final thing we can do now that we know molar volume is we can find the density of gases. Now, this funny letter here is the Greek letter rho, and that stands for density. So the density of a gas equals molar mass over molar volume. So a problem we might have is an unknown diatomic gas has a density of 0.0902 grams per liter at STP. What is its molar mass? So here's our formula, density, molar mass, molar volume. Now we're looking for molar mass, but we were given the density, and molar volume is always the same for everything at STP. So we can substitute in our density of 0.0902 grams per liter, put in 22.4 liters for the molar volume, rearrange the equation, dividing both sides by 22.4. So we get 0.0902 grams per liter times 22.4. I did say multiply, didn't I? Not, if I said divide, I meant multiply. Sorry about that. I'm not sure what I said. Multiplying both sides. Now, liters cancel out because one's above the line, one is below the division line. So we get a molar mass of 2.02 grams. Now, we can actually figure out what the gas is because we know it's diatomic. So since this is the molar mass of a diatomic molecule, divide by 2 to find the mass of one atom. When we do that, we find the mass is 1.01 grams. If we look that up on our periodic table, we find that that is hydrogen. So the gas is in fact H2. Okay, so you can actually, if you know the density of a gas, you can use this calculation to figure out what it is. So our objectives for this video were to state the law of combining volumes, explain why the kinetic molecular theory is limited in its ability to describe real gases, use the ideal gas law to perform calculations, and predict the amount of gas in a chemical reaction by using stoichiometric calculations. This is it for the chapter. You have everything you need to know to start studying for the test and to do all of the problems expected of you.